Hi guys, we're back to talk more about stratigraphy, and this time we're going to focus on correlation. So we mentioned this briefly before, but I want to go through it in a little bit more detail. And basically the idea of correlation is basically figuring out how different layers are related to layers or are correlated with layers that are in other areas. So sometimes we might have two layers that are right near each other that match, and so those are a little bit easier to place together. But we might have layers that exist across regions, and then they may be interrupted. So they might not be like contiguous across a region, but we may think that they are potentially part of the same similar layer from the past. But we want to do some correlation exercises to help us understand if in fact they are correlated or not. So let's look at some slides to help us understand this. So basically there's kind of two different sets of techniques that we can use to try to kind of correlate layers across space. And so the first technique is lithologic correlation. So lith refers to rock. And so in this case, we're actually just matching up different rock layers. So a limestone layer with a limestone layer, a sandstone layer with a sandstone layer, and then even more specifically, we might have, limestone layers with a certain kind of level of grittiness or amount of fossilization, or sandstone layers with particular coloration, like a pinker colored sand or a siltier sand or things like that. So we're looking for these kind of matching types of rocks, and that's called lithologic correlation. And so lithologic correlation is pretty successful over relatively small regional areas, so areas spanning about several miles. And so we might have a couple different units. So you can see here, these are these different kind of like stratigraphic columns that are cut out from three different locations across the landscape, like A, B, and C. And they're not necessarily going to be exactly the same. And there might be some different reasons why they aren't the same. Maybe the areas were having slightly different environments at the time that they were forming. So maybe one of these areas was submerged underneath the ocean and one wasn't, or one was on a steeper slope and one was on a flatter ground. So there can be differences in the way that the original layers formed. But then also, as we've talked about before, there is this idea of what's called an unconformity, where there's basically a time gap in between two layers that touch each other. So over here on the far right-hand side, we can see that there is this, what's a sandstone layer here, and then like a shale layer up here. And it appears that those two layers are not matching up in ages. So there's the historical period of time where there's no rock record. And that's true in this location C, but it's not true in location B and A. And so what we know is that this must represent an unconformity, this kind of missing piece of data. And so what that's common, we'll see across the landscape is that we'll have maybe similar layers that might be correlated between different columns. But maybe we'll have certain layers that we refer to as being pinched out that don't exist in one of those columns or more than one of those columns. And that's often going to represent some sort of unconformity there. And then it's also important to note that the layers often have different thicknesses in different locations. So like the shale layer or the sandstone layer is thicker over in A relative to B and C. And that's just also maybe because of the difference in position where these three locations were on the landstone at the time that the sand was accumulating there. And so one was kind of leading to like a deeper accumulation of sediment. And so you can see how this might look on the landscape in the picture down here. Okay, so lithologic correlation is matching up the rocks. And so lithologic correlation is a great place to start. However, if you're only looking at rocks, then you may be missing information, and especially your ability to match up rocks and assume that they match, with another rock of the same type really starts to fall apart over longer distances. So this lithologic correlation is going to be much better on a smaller spatial scale, and as the spaces widen, you want to look for other markers that help. So things like fossils are going to be a great kind of additional piece of information that can help you kind of figure out how layers are truly correlated. So in this particular example, we have these two kind of stratigraphic columns here, and we have different kinds of layers that represent different types of rock. So in general, these brick type pattern represents limestones. The kind of horizontal dashing pattern represents shales, and then the dotted pattern represents sandstones. Those are just kind of common geologic symbols. And so you might start to look here and think like, oh, okay, well, here's a limestone and here's a limestone. So maybe those are the same, 6 up here and 4 down here. Here's a sandstone and here's a sandstone. So maybe those are the same. But then if you start to look a little bit deeper and look for particular fossils, and we see that certain fossils exist in layer 6 here and layer 6 here, even though this layer is a limestone layer and this layer is a shale layer, then we might have to rethink our original way that we would have tried to correlate these layers if the lithologic information was the only information that we have. So we know that fossils represent organisms that lived in kind of discrete periods of time in history. And so if we have fossils that are kind of unique to one layer here and then unique to one layer over here, then that's probably an even better marker than just looking at kind of rock outcrops or lithologic correlation alone. So in general, lithologic correlation is using rocks, and it can be appropriate on the scale of up to about several miles. But then if we want to do correlation beyond that, lithologic information can provide one layer of information, but we're going to really want to move to fossils, and we're going to want to do some fossil correlation to help us have more accurate correlation over larger spatial scales. Okay, so when we're matching fossils, basically we're using this principle that's sometimes called the law or principle of faunal or fossil succession. And succession, right, is the idea of like what comes after something before it. Like in the monarchy, there's the succession of the crown or whatever. So we have, or we know that there's a very consistent and determinable order in which fossils occur vertically within layers of rock. Okay, so that's something that was noticed pretty early on, even before people understood that extinction was something that happens, right? That's a kind of a pretty intuitive thing that we understand now, but was not necessarily well known hundreds of years ago. But even at that time, they recognized that there were these distinct fossils that appeared and then they disappeared. And once they disappeared, they didn't come back. And so by having this distinct, determinable, predictable way in which fossils appear and disappear can help us kind of track what period of time the different rocks we're forming in that contains these different fossils, because we know that the fossils are kind of matched to these discrete periods of time. So here are, here's a list of the different geologic time periods. We haven't gone into this in great detail yet, but we know there's eons, like the Archean, Proterozoic, and Phanerozoic eon. Then we know there's eras, like the Paleozoic, Mesozoic, and Cenozoic. Then we know there's periods within those and epochs within those, and we'll get into this in much more detail later. But there's very specific fossils that exist within specific rock layers that form in specific periods of time. And in particular, index fossils are these fossils that are widely geographically distributed. So we see them in many different places, but occurred over a relatively narrow period of geologic time. And so when we see them in a place, it helps us understand that rock layer must have formed during that limited period of geologic time. So maybe like during the Miocene or during the Jurassic. And if they're widely spread enough geographically, then we might see those same marker or index fossils in many different places across the landscape. And so it can help us match up the rock layers from disparate places across the landscape with similar like marks or stamps in terms of time. So there's lots of different kinds of index fossils. Things like ammonites or trilobites are common fossils that represent very specific eras in geologic history. But you can also really get a lot of super detailed information. So foraminifera are types of plankton that live in the ocean, commonly referred to as forams. And these evolved over time to form slightly different kinds of forms. And when these different forms existed, we can recognize that they match to very specific periods of geologic history. So we can look for these very specific fossil patterns in the rock. And then when we see them, we can say, oh, this rock formation must have occurred during the Cretaceous, during the Jurassic, during the Triassic, etc. So basically, once we have that kind of information and we know that there's these specific index fossils that represent specific periods of history, then we can go to the rock record and we can start out by trying to look at different lithologic patterns that may match up with each other. But then we can look deeper and we can look at these specific kinds of index fossils and can help us confirm or potentially dispute the kinds of assumptions that we had about the ways that different rock layers would match up. So for instance, across the Southwest, there's some similar layers that exist in, across that region. So the Grand Canyon in Arizona, and then the Las Vegas in Southern Nevada have some similar layers, although there's kind of a lot deeper layers in the Las Vegas area compared to the Grand Canyon area. But we can look at the kind of Monte Cristo limestone formations outside Las Vegas and the Red Wall limestone formations in the Grand Canyon. We can find similar fossils that correlate between those two layers, and then it can help confirm that in fact the limestone that formed as part of the Red Wall formation in the Grand Canyon and the Monte Cristo formation in Las Vegas were in fact forming at the same time. So they're correlated. And this is kind of a way to look at this as a cross-sectional diagram across space with kind of the Grand Canyon here and then Las Vegas over here. So here's just another view of the Southwest in cross-section, right? So if we could cut down into the mountains and into the landscape and look at it from the side, we would see this kind of bedrock, the schist bedrock material down below. We would see some of these magma chambers, old magma chambers that have cooled to kind of granitic forms down here. We can see some old faults that have occurred, but then we can see some similar layers that may not have similar thicknesses, but kind of exist across the landscape. So we have a great view of them in the Grand Canyon where there's this deep cut through many layers, but then we can also see some of these layers exposed in places like Zion Canyon, Bryce Canyon, Vermilion Cliffs, etc. But depending on where the particular spot on the landscape is, certain layers may be exposed or not exposed. So over here in the area of the Grand Canyon, there's not as many of these surface layers as are still visible in places like Bryce Canyon or Zion Canyon. So you're going to have kind of different pieces that may match up with each other. And so we can do an interesting exercise in terms of correlating these layers, even though they're not necessarily exactly the same. And this is, again, going to be an exercise in matching both lithology, the rocks, as well as using fossil evidence to help us kind of narrow down and confirm the ideas that we have. So anyway, this is just another way to kind of look at these three places, Bryce, Zion, the Grand Canyon. So the Grand Canyon is kind of the deepest part. I'll go back for 1 second, right? It's cutting all the way down deep into this layer and it doesn't have as much of the surface layers, right? So that's the Grand Canyon. Then Zion is some of the upper layers of the Grand Canyon with some of the lower layers of Bryce. And then Bryce is some of the upper layers of the, or lower upper layers of the Bryce, Zion Canyon with some other layers that don't exist in the other areas. So with all our tools, we can help kind of correlate these across the landscape to make a more complete picture. Okay, that's a good stopping point.